with some examples of modern physics. So we'll start with a question based on the first topic of modern physics, photoelectric effect, through which we'll cover the various different aspects of numerical calculations in photoelectric effect. So let's say we have this kind of situation where we have a standard photoelectric effect experiment, wherein we have the cathode and anode inside a vacuumized tube. Potential difference V in general like this, and monochromatic light incident on the cathode like this. So let's see how we can calculate the various aspects of the photoelectric current and all that using this information. So given monochromatic light of wavelength lambda such that hc by lambda is, let us say, 2.4 electron volts, is incident on a metallic cathode, on a metallic plate of area say 20 centimeters square at an intensity let us say 2 watts per meter square. The work function for the metal of the cathode that is given to us as 2.0 electron volts, and the efficiency of photoelectron generation is equal to 10 raised power minus 4. That means 1 in 10,000 photons actually generates a photoelectron because of probabilistic factors. So even though every photon has an energy greater than the work function, so every photon is capable of generating a photoelectron, but only 1 in 10,000 generates a photoelectron because of the various probabilistic factors involved. Okay. So efficiency of photoelectron generation, it is that. Okay. So from all this information, now we have to find maximum kinetic energy for a photoelectron stopping potential and saturation current to determine these factors. So just try out this. We'll discuss the basics involved, but Yeah, people, you can start sending me the answers. Yes, Bhaskar. The answers seem correct. Just check the unit of the saturation current once more. Okay, people. So let's check out the whole working. So what you have to understand here is that maximum kinetic energy for a photoelectron will be energy of the photon minus the work function, or hc by lambda minus the work function, which in this case is 0.4 electron volts. So your stopping potential is the voltage required to stop this kind of electron. So your stopping potential should be such that electronic charge into stopping potential is equal to the maximum kinetic energy. So that is why your stopping potential becomes this value only, but in volts, because you're dividing this by charge of electron. So you know that 1 electron volt equals to 1 into in terms of joules. Therefore, 1 electron volt divided by coulombs is nothing but 1 volt. So this is a simple calculation. And then we come to the saturation photocurrent. Okay. So as you know, your graph of photocurrent versus voltage is of this type. It reaches a saturation beyond a certain voltage. whereas it is stopped for a certain negative voltage. So this saturation photocurrent occurs when the entire flux of photoelectrons generated is swept away to the anode. None of the photoelectrons generated are finding their way back to the cathode because of collisions, etc. There is sufficient voltage to sweep away the entire flux or entire flow of photoelectrons created. So basically what we have to do is saturation current corresponds to the flux of photoelectrons generated. So that is going to be nothing but the probability factor multiplied by the flux of photons incident. This is the efficiency part. So in this case, that efficiency was 1 in 10,000. So 10 raised power minus 4 into, let's say, dn by dt, where this is number of photons incident on the cathode per unit time. And of course, we're converting that into a current, so that will be multiplied by electron charge. So efficiency into number of photons incident per unit time. This quantity will give you number of photoelectrons generated per unit time. So that into charge of photoelectron will give you charge generated per unit time. So that is nothing but the saturation. So this is the logic of this calculation. So now the next thing you have to think is how you will calculate this thing. How you will calculate this. Now for this, you know intensity. Intensity is energy incident per unit time per unit element. And you know area of the plate. This is known, intensity is known. And you know the energy of the photon. This is known. So you see how you will use these three to generate this quantity, dn by dt. That is number of photons incident on the cathode per unit time on the surface of the cathode. And then you multiply with that with efficiency. So that will tell you the number of photoelectrons generated per second. So number of photoelectrons generated per second is equivalent to the saturation current. So basically, you have to multiply this flux with electronic charge, of course. That will give you the value of saturation current. So now you have to just work out how you will calculate this thing. dn by dt, the number of photoelectrons incident per unit time. Okay, so yeah, more people have got the answers. So, let's check. So the intensity is given as 2 watts per meter square, and the area of the plate is given as 20 centimeters square, and so 2.4 electron volts. So intensity is 2 watts per meter square. Area of the plate is 20 centimeters square. Therefore, energy incident per unit time or power incident, that will become intensity into area. So 2 into 20 into 10 raised power minus 4. This will be in watts. Therefore, photon flux incident, that is number of photons incident per unit time, that will become this divided by energy of the photon. 4 into 10 raised power minus 3 divided by 2.4 electron volts. This is in watts. We have to convert this into electronic charge. So convert this into joules. This is in per second. This is your photon flux per second. So next, your photoelectron flux. That is number of photoelectrons per second. So that is your probability factor multiplied by the photon flux. That will become when E is just 1.6 into 10 raised power minus 9. This is so much per second. So finally, your saturation current is the photoelectron flux multiplied by electronic charge. So it is so it is 4 upon 2.4 into 10 raised power minus 7 amperes. So that will become how much? Microamperes. Approximately 6. I just check my calculation people, but this is the general method of. Okay, understood. So the value is clear, people. Okay, good. Now let's see another version of this type of situation. So now we have this situation. We have a metallic sphere. Of radius capital R and work function phi. And somewhere far from it, we have a point source of monochromatic light. This is a point source. Wavelength of light lambda and power p. So these two terms are given to us. Now the center to center distance from this to the sphere so the center to center distance is small r. I mean the point to the center of the sphere, where small r is comparatively large in terms of order of magnitude compared to capital R. So at t equal to 0, the point source starts emitting. Right. So if hc by lambda is greater than the work function and the efficiency of photoelectron generation is n, then find the charge of the sphere as a function of time. And the time at which photoelectrons stop escaping from the metal surface. For both of these parts, we have to assume that photoelectrons generated escape to infinity. No, n is just a probability factor, like 10 raised power minus 4 that time. It's not expressed as a percentage, it's just a factor. Okay, Ananya, n is just like in the previous question, we had given n's value as 10 raised power minus 4, like that, it's a probability factor. It can, of course, be given in percentage also, but in this case, it's not given in percentage. Okay, so here you have to get everything parametrically instead of values. So the first thing you have to consider is what is the intensity which is incident on the surface of the sphere. So that is where a bit of waves type of concept comes in. That because the sphere is small in size, I mean compared to the distance from the point source. Okay, I'll check your answer. So what will happen is you have to consider like a spherical surface of radius capital R. So at a distance capital R from the source, the intensity becomes power divided by 4 pi r square. And because this is very far away, this thing, so you have to also consider the solid angle subtended by this as basically the solid angle subtended by a disk. So you have to consider this like, so the power incident will be approximately intensity multiplied by pi capital R. Because you're like taking a projection of the hemispheric on this radial line. Okay. So basically what you're assuming is because it's very far away. So you're assuming something like this because it's very far away from the point source. So your incident light is almost like straight lines. Almost like a plane wave incident. So this surface, this projection on this becomes like a disk. So surface area projected on a plane perpendicular to the incident beam. That becomes pi r square. And the intensity of this light is tending to that power upon 4 pi r square. So the incident power is dE by dt. This kind of thing. So it becomes power of the source upon 4 pi small r square into pi capital R square. So this is your energy incident per unit time. And rest of the calculation is similar to this one. So hope this is clear people. This concept over here. So I'll just minimize this again. Yes, so we will need the photon flux because from that only we'll get the electron flux. And from the electron flux only we will calculate the charge as a function of time. Correct? So photon flux that will become incident power by this. this. So photoelectron flux, that becomes equal to the probability factor, the number of photoelectrons generated per unit time. Okay, this. So charge of the sphere Q at time t. This becomes the charge as a function. Yes, Bhaskar, you got all this correct. Okay. So now we come to the last part. If you got the charge as a function of time, then when will the electron stop escaping? So what is happening? The potential of the surface, the metallic sphere's potential becomes 1 by 4 pi epsilon naught Q by R. And the moment the potential becomes greater than equal to the stopping potential, electrons stop escaping. So 1 by 4 pi epsilon naught into that Q, which was N into E into lambda into P into R square by 4 small r square hc. This whole factor into time. And there will be another capital R in the denominator, so this square will cancel out. So this will be the potential. This becomes greater than equal to hc by lambda minus work function. And this happens. This will give you the condition for photoelectrons to stop get generated. So this was a little bit of additional concept. Okay, so hope this is clear, people. Okay, good. Now let's look at a question based on structure of atom, Bohr's model, that kind of thing. So what is happening is we have monochromatic light incident on, let's say, a hydrogen like element. Now this starts radiating. So the radiations observed are of three distinct wavelengths. Such that the incident light of wavelength lambda matches the longest of the three wavelengths emitted in terms of wavelength. So if lambda equals 27 by 20 times lambda naught, where lambda naught is the wavelength of the first line of Lyman series for hydrogen atom, then find Z for the hydrogen-like element and the initial state and the excited state. This element has. So what kind of state it was in before the light is incident on it and what kind of excitation it achieves. So monochromatic light of wavelength lambda is incident on some hydrogen-like element, and as a result of that incidence, radiations observed are of three distinct wavelengths. The longest of the three wavelengths matches the wavelength of the incident radiation, and that is equal to 27 by 20 times the wavelength of first line of Lyman series of hydrogen. So from this data, we have to back calculate and find this thing. What is the Z for the hydrogen-like element, and what is also its initial state as well as its excited state. Anybody got the answer for Z? Okay, let's go with this question. First, let's talk about interpretation. What is this information telling me? 3 wavelengths are emitted. इसका क्या मतलब है? Yes, Chakshu, your answer is correct. What is the meaning of this? That 3 wavelengths are emitted. Okay, let's understand this. So, suppose, yes, Chakshu, that is correct. Okay. So let me explain to everybody. So suppose these are your energy levels. Now, suppose you're going from some EM-1 to EN-1, where N is greater than E. So that means you are undergoing a transition like this. The electron is undergoing a transition like this. So the incident photon must have this kind of energy. So that is there, of course. So there is this formula Z square into 13.6, 1 upon N square minus, or rather here 1 upon M square. Minus 1 upon N square. That will be your Hc by lambda. But also it means that, okay, also it means that on reaching the excited state N equal to N, it can relax back to N minus 1 or N minus 2 or up to ground state. Okay. Then from N minus 1 to N minus 2, like this. So basically, on reaching that excited state N equal to N, it can give NC2 transitions are possible. So for example, if N is equal to 4, that is, it excites to the third excited state, okay, then the number of transitions possible for relaxation or de-excitation is 4C2 or 6. So be like this. So it could do this, 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 and it could do this. You can see that 6 different wavelengths corresponding to Hc by lambda equal to E3 minus E2, E3 minus E1, E3 minus E0, E2 minus E1, E2 minus E0, and E1 minus E2. These are all the 6 wavelengths which are possible, of which you can see that this one will be the minimum energy, so maximum lambda, okay, and this one will be the maximum energy, so minimum wavelength. Okay. So here, of course, it is not 6 different transitions. In this particular question, it is 3 different transitions. So to understand the excited state, you have to use that formula NC. Understand? So this formula becomes very important. So in this particular question, there are 3 distinct wavelengths emitted. That means your NC2 is equal to 3. So n into n minus 1 by 2 is equal to 3. That means n is equal to 3. So that means the excited state will be E. This will be the excited state. So now from this you back calculate and you will get the value of set. Just try this sort of. Chakshu and Bhaskar have already got it. Z will not be 1 meter. Okay, let me do the calculation. So we understand that now what is happening is this is some kind of element which has Z unknown. Okay, and initial state M that is also unknown. And now some kind of light of wavelength lambda is incident on it. Now this lambda equals to 27 by 20 times lambda naught compared to that Lyman series of hydrogen atoms. Now from this we are getting 3 different wavelengths. We are getting some lambda 1, lambda 2 and lambda 3. So that means, so 3 different wavelengths means that the excited state is n equal to 3 or E2. Okay. And let's say Hc by lambda 1 is E2 minus E0. Hc by lambda 2 is E1 minus E0. And Hc by lambda 3 is E2 minus E1. You can see that this is the minimum energy and this is the maximum energy. So that means this is the shortest wavelength and this is the longest wavelength. Now it says that this lambda incident matches which one? The longest one. So lambda incident matches the longest of the 3 emitted. Yes, it is correct now. So that means lambda equals to lambda. So that means hc by lambda equals to hc by lambda 3, which is E2 minus E1 for this. Okay. So hc by lambda equals z square into 13.6 into 1 by 2 square, 1 minus 1 by 3 square. And it is given to you. Lambda is 27 by 20 times lambda naught. So that means hc by lambda naught is equal to 13.6 into 1 minus 1 by 4. So now you relate these two equations. This and this. So lambda by lambda naught equals to 27 by 20. So you just divide this by this. So 13.6 into 3 by 4 divided by z square into 13.6 into 5 by 36. So from this you will get the value of z square. 27 by 20 equals to 3 by 4 into 36 by 5 into 1 by z square. 20 cancels out, 9 cancels out, 4 cancels out. You can see that z square is equal to 4. So z is equal to, that is helium. And also, since lambda is equal to lambda 3 or hc by lambda equals to z square into 13.6 into 1 by 3 square minus 1 by 2 square. That is telling you that the initial state is n equal to 2 of E1, the first excited state. Okay. So this material was helium plus in first excited state. This becomes our final answer. Okay, so most of you got this correct, but I hope it is clear to everybody. The method. Yeah. So it is going from initial state beta, Bhaskar will be this one, no? It's absorbing this lambda, which is taking it from E1 to E2 or n equal to 2 to n equal to 3. So longest wavelength, so minimum energy. See, E0, E1. Now it's going here, but through the shortest possible wavelength. So that means initially it must have been here. When hc by lambda was incident on it, it made this transition. That's how this wavelength equals this energy. Minimum energy or maximum wavelength. So the incident lambda, got it? So that's also important. The incident lambda agar bola hota, it is the shortest wavelength, then ulta hota. Then the initial state would have been the ground state. But then even this formula would have been different. Hc by lambda would have been 1 by 1 minus 1 by 3 square, not 1 by 2 square minus 1 by 3 square. Okay, so this is just few questions of your modern physics. So you can cover some more questions from these two chapters, and then next time again we'll pick up the next two chapters of modern physics, which is nuclear physics and X-rays. So again, the typical thing in X-rays will be the calculation of the alpha beta parameters for the Moseley's law, how you do that using shielding coefficient and all that. And modern nuclear physics, there are various things including disintegration law and second order differential equation and all that. So we'll discuss some of those later. Now let's come back to some of the other questions that we had in our set. So one of the questions from the doubts you've been asking that I wanted to discuss in detail is this one. You had that circular disc which was given a spin of, let's say, omega naught, and then placed on a surface such that that surface has something like this. You placed it on a surface where on a horizontal surface where this part has some different coefficient of friction and this part has some different coefficient of friction. So basically like this disc, while it is spinning, was given us initial spin omega naught like this and placed on a two-dimensional surface. Now such that that surface itself has two halves. One half has a different coefficient of friction and the other half has a different coefficient of friction. And the disc is placed such that the border of the two regions that falls, so if you're seeing this from the top, that surface has lambda 1 in this region, lambda 2 in this region. Now the disc is placed such that that border falls along the diameter of the disc. So you have to find the initial acceleration and the angular acceleration of the disc the moment you place it. Okay, so this was the question. So the disc given omega naught about its vertical symmetry axis is placed on a surface such that its a left half experiences friction with coefficient of kinetic friction equal to mu2 and right half mu is equal to mu1. So we wanted to find the acceleration of the center of mass. So the execution of this problem is not that difficult. The concept is a little more complicated. So what we have to understand here is, given this disk, now also let's draw the symmetry lines. Now consider a circular ring as a differential element on the disk. Let's consider a circular ring which is of radius r and thickness dr. Now remember, this is rotating like this, the initial state. So if you now consider an element on the circular ring at a position theta, and therefore of a thickness RD. So that small section has an area which we can write as delta A of this thickness multiplied by the thickness of the ring. So it's basically like this. On the ring, that element is like this. This thickness is dr, and this thickness is RD theta. That element, an area like this. So it has a mass of sigma into delta A. So m into pi upon pi r square into r dr d. So that is now going to be experiencing a frictional force in this sort of direction. This will experience a tangential frictional force. In this sort of direction. That frictional force, let's say dF1, will be mu1 into delta m. So that frictional force will be mu1 into m upon pi r square into r dr. Now you'll see the reason why the net friction doesn't become zero is now you see the diametrically opposite element, which is here. This element will experience a force in exactly the opposite direction, but the magnitude of that force will not be the same. This will experience a force in this sort of direction. And this force is dF2. Okay. Good. So Bhaskar, you got this question. That's fine. Now I'm just stating it to the others. Okay. So you can see that these two forces together will create some net horizontal as well as some net vertical force. But out of that, something will cancel. I mean, horizontal vertical means both are in the horizontal plane. If we take this as our x-axis and this as a y-axis, so xy is the horizontal plane. Gravity is going into the plane, so it is minus the plane in this diagram. Okay. So you will see that the vector sum of F1 and F2 in this diagram the net force because of these two forces is dF1 plus dF2. So that will become, now we can see that this is making theta with a vertical and this is making theta with a vertical. So it is going to become dF2 minus dF1 sin theta j cap plus dF1 minus dF2. Oh, sorry. So this force dF1 like this at theta with the vertical. On the other side, that force dF2 at theta with the vertical. These angles were theta. So it becomes dF1 minus dF2 cos theta I cap plus dF2 minus dF1 sin theta I cap. this becomes the x component of frictional force. And similarly, the y component of frictional force becomes. Okay. So now we will substitute that delta m and first integrate theta from. Now remember, we are taking a pair of elements. So we'll have to just integrate theta from here to here. We'll integrate theta from minus pi by 2 to plus pi by 2. Okay. So that will give me the net force acting on a ring. And then we'll integrate with respect to r, small r, from 0 to capital R. That will tell me for all the rings integrated for the disk. No, the reason why we cannot do the center of mass concept over here is because moment arm is also involved. And all the forces are acting in different directions. So now my net friction's x component will become this summation of this delta fx. So that will become integration first of cos theta. Now that delta m was m upon pi r square r dr d theta into g. So first we'll integrate this from theta equal to minus pi by 2 to theta equal to pi by 2. And then integrate it for all the rings going from 0 to capital R. That becomes the next step. So the x component of friction becomes this. So this will give you a factor of 2. This is becoming the x component. Now similarly, when you calculate the y component of friction, you will see it will come out to be 0. And we can logically justify that also why it comes out to be 0. The y component, I'll just explain in a moment. The y component you can see comes out to be 0 because if you now consider on the ring, if you consider one element here and one element here, so you can see these frictions are equal in magnitude. Oh, sorry, I made the mistake. This was sine theta. See, the x component is sine theta. My mistake. So, just a minute. So, it's the x component which will come out to be 0. The y component which will come out to be. So I'm just marking the correction here with red so that you are aware of it. So the x component you can see is sine theta. Is the angle with the vertical which is theta. So this is sine theta, and this one is cos theta. So you'll see that what we have calculated is actually the y component. I should come with mu2 minus mu1. Or let's just do this correction. This one will be sine theta. So when you do the integration, this one will come out to be 0. You have this sine theta d theta value. So this will come out to be 0. This will come out to be 0. So the x component will come out to be 0. Whereas the y component will come out to be non-zero. So this you can see is df2 minus df1 cos theta. This minus this. So it is mu2 minus mu1 delta in v cos theta. So this is going to be to carry out all those same steps, and you will see this one will come out to be the non-zero quantity. So carrying out all the steps, you get this is mu2 minus mu1 mg by pi. Whereas the x component would have come out to be 0. Now the justification why the x component is coming out 0 here is like this, that so again within this when you consider that ring kind of element, now consider 4 elements on the ring. Consider 4 elements on the ring which are at these kind of positions. Theta, theta, theta. Now this one and this one are experiencing the same coefficient of friction. So it was rotating like this. So df1 and df2. So see the x components are cancelling. Okay. This one and this one are experiencing same amount of friction. So you can see that in pairs their x components are cancelling. Okay. Whereas their y components for df2 and df2 are adding, and df1 and df1 are adding. So df2's y component and df1's y component, they are in opposite directions. So that is why the net force it will experience will be along this line. ACM will be AY, and that AY will be equal to the net y component of friction divided by mass. In this case, it will come out to be mu2 minus mu1 by pi into G. Okay, so this is a proper application of double integration. This is how we are doing the element breakdown. So Chakshu, the thing is that we cannot use center of mass here because what is happening on the different DMs, the friction is acting in different directions. So in my integration, actually, I only considered this pair, not the 4 particles that I saw earlier. This pair I've considered. So because I'm taking a pair at a time, so I'm integrating only half the disk. The theta from minus pi by 2 to plus pi by 2. Okay, so the final calculation, the steps of the integration, this 0 for this one and non-zero for this one. So finally, the logical understanding also why the x component becomes 0. You can see that by considering 4 symmetrical elements instead of 2 at a time. That is finally over here. You can see that if you take a pair of, on one side, these two df1s, you can see that their x components cancel, but their y components add to give you a net downward force. And you take these two, again their x components cancel, but their y components add to give a net in the upward direction. Now, because this is not equal to this, ultimately the y components are not cancelling. So that is why the center of mass here will experience an upward acceleration. Alright, now another thing I wanted to discuss with you people based on question which I saw you were discussing in the group, and more I want to discuss like a shortcut method of solving this kind of problem is this. You had the two bodies connected by a spring and you are applying force from one side and you want to find maximum elongation of the spring or maximum acceleration of the blocks and all that. This is mass M1, this is mass M2, and initially both are at rest. The x of the spring is 0, and at t equal to 0 we start applying a constant horizontal force. This one is start applying a constant force. So the easy way to do this type of question is SHM by looking at the free body diagram in center of mass. So what happens here is in center of mass frame, which is a non-inertial frame traveling with acceleration equal to F0 upon M1 plus M2. So in this frame, if we look at the free body diagram, at some time t. So by that time, what has happened? The spring has elongated a little. So this block and this block. They are experiencing forces which are spring force, pseudo force, external force, and spring force and pseudo force. So M1 DC dx, dx M2 AC. External force, and with respect to center of mass, they have, let's say, an acceleration E1 and an acceleration E2. Just a moment, I'll reshare this because I'm getting an error on the board. Just hang on a second. Restart the program. Yeah, so E1 and E2 are with respect to center of mass. So with respect to center of mass, let's say this block is displaced by x1 and this block is displaced by x2. So E1 is minus d2x1 by dt square and E2 is minus d2x2 by dt square. And you can see that x is equal to x1 plus x2 and m1 x1 will be equal to m2 x2. So in the center of mass frame, the center of mass is not moving, okay? Because remember x1 and x2 are also with respect to center of mass. So all these parameters E1, E2, x1, x2, they are with respect to center of mass frame. And in this frame, what is happening? the displacement of the center of mass is 0. The acceleration of the center of mass is 0 in this one. So that's why we have this equation. Okay. So x1 can be written as m2 upon m1 plus m2 times x. And x2 can be written as m1 upon m1 plus m2 times x. So we have these equations. Now coming back to the free body diagram, you can see the equations will give you that secondary type of SHM equation. Okay. So for the block M1, you can see that Kx minus M1 ACM is equal to M1 E1. And for the block M2, you can see Kx plus M2 ACM minus F0 is equal to M2. So this is the third and the fourth equation. Now when you substitute the constraint between x and x1, okay, the third equation can be modified to, so this equation will get modified to k into m1 plus m2 upon m2 x1 minus m1 ACM will just become m1 f0 upon m1 plus m2 is equal to minus m1 d2 x1 by dt square, or that d2 x1 by dt square is minus omega square x1 plus f0 upon m1 plus m2, where omega square you see will have your reduced mass term. Omega square will be E by mu, where mu is m1 m2 upon m1 plus m2. This is what your equation 3 will reduce to when you substitute the constraints on it, which is from equation 1. Just substitute the condition from equation 1 into equation 3. This and that will give this condition. Similarly, do for equation 4 and you will get we can discuss that also. But actually, reduced mass is the easiest method to understand these type of problems. Okay, so hope this equation is clear now. This final form of equation 3 that we got. Now, similarly, we want to substitute this thing, equation 2 into this, and reduce that into a final equation. So we will get, so this equation 4 will become k into x, which we'll now write in terms of x2. So it will become n1 plus m2, x2 by n1, plus m2 f0 upon m1 plus m2 minus f0 will become m2 into minus d2 x2 by dt. So again you will see that you will get your d2 x2 by dt square as minus omega square x2 plus a certain term. Now that term here will become like this. This term will be minus m1 upon m1 plus m2. Then you are dividing that with m2. With minus m2. So it will become plus of m1 by m2, m1 plus m2 become this kind of. So we are seeing where again your omega square is the same. So both these equations, they are what we call the modified form of SHM. The modified form of SHM is where your equilibrium is not at x equal to 0. If we have an equation where d2x by dt square is equal to minus omega square x plus some constant. This basically means that x is equal to e sine omega t plus phi plus c by omega. This is what it is. Because you can see from here that 2x by dt square is minus a omega square sine omega t plus phi, which can be written as minus omega square x. That is this thing plus c by omega. This is basically this. And so here what is happening, that first equation that we got for block M1, we got d2x1 by dt square is minus omega square x1 plus some constant, let's call that c1, and that constant was f0 upon m1 plus m2. So that means my x1 will be some amplitude into sine omega t plus some phase constant plus c1 by omega square. Or let's write this whole constant as something else. So it is x1 plus, let's write this as something y1, where y1 is a constant, or something else, let's say b1, where b1 is a constant. Now, how to find amplitude, phase constant, and that b1? Now, from that we can see at t equal to 0, x was 0 and dx by dt was 0. So that means x1 equal to x2 was 0 at t equal to 0, and v1 equal to v2 was 0. Both the blocks started from rest in the center of mass. So that means what is happening is x1 at t equal to 0, which is a1 sine phi 1 plus b1 to be 0, okay, and dx1 by dt at t equal to 0, which is e1 omega cos phi 1. So now this will give us everything that we require. So we can see that cos phi 1 is 0 and sine phi 1 is a negative quantity. So that means phi 1 is minus phi 1. Okay. And minus a1 plus b1 is equal to 0. So a1 is equal to b1, which is equal to basically c1 by omega square. So that is nothing but f0 upon m1 plus m2, okay, divided by omega square. So we can write that as e by mu. So the amplitude of oscillation for this block is this one. It is m1 m2 upon m1 plus m2 whole square e. This is the amplitude of oscillation for this block. And from this equation, you can also understand that this x1 so this x1 will ultimately come out to be like this. It will come out to be a1 into 1 minus cos omega. Where a1 is equal to this. You can see this is a dimensionless factor and this is dimension of force upon k, so it's the dimension of length. So x1 varies between 0 and 2a. It's 0 at t equal to 0 and it becomes 2a1 at t equal to half the time period. And again t, again 3t by 2. So now you can understand that if you are treating the center of mass like a wall, with respect to that wall, this block is doing this. It's going x1 in this direction. So the center of mass is like a wall. So with respect to that, this block is doing x1. So it's going from 0 to 2a1 and back. And similarly, the other one on the other side will be doing an x2. So the maximum extension of the spring will actually become 2a1 plus 2a. Because simultaneously both blocks are having the maximum x from the center of mass. Okay, so I'll just take you through the above steps once. And now you try to repeat those steps for the second block yourself. And I'll put the final answer. Okay. So we'll come back to this. Now let's focus on this thing. How we solve an equation of this type. Whenever we have an equation of this type, this is like a modified SHM with equilibrium position at x equal to c by omega square and x varying between 0 and 2 times c by omega square. I mean, not necessarily this, but the equilibrium is always at c by omega square. Because equilibrium is where you can see acceleration is 0. So this sine omega t plus phi term should be equal to 0. When that happens, x's value is how much? C by omega square. So that's the difference between this equation and the more standard equation where x is equal to a sine omega t plus phi. This is the standard SHM where x equal to 0 is the equilibrium position. This is the modified SHM minus omega square x plus c where the equilibrium is at c by omega square. Okay, so having identified that equation, the M1's equation of that type, further how do we solve? And most importantly, how do we solve for this constant C1 and this phase constant phi1, always using the initial conditions. So what are the initial conditions? I know these are the initial conditions. That at t equal to 0, the spring started from natural length. So x1 and x2 were both 0. And both the blocks were at rest. So dx1 by dt is also 0. And dx2 by dt is also. Okay, now use the same technique to solve for x2 also. Okay, so from that we'll get the range of the second block's motion with respect to the center of mass. Okay, so the second block's equation you can see is like this. Very similar. So that C2 was so this tells us that x2 as a term. Right. Now solving this at p equal to 0, the value of x2 should be 0 and the value of dx2 by dt should be 0. So that means a2 sine phi plus c2 by omega square and a2 omega cos phi 2. So from both of these, you can see that phi 2 will be minus phi by 2 and minus a2 plus c2 by omega square. So your a2 is equal to v2 or c2 by omega square. And for x2 as a function of time will be a2 into 1 minus cos omega t. Okay. So now you can see x of the spring is x1 plus x2. So x of the spring actually just becomes a1 plus a2 into 1 minus cos omega. So maximum extension just becomes 2 times a1 plus a2. where A1 and A2 you have calculated. Okay, so the way to relate this with your regular simple SHM of single block is like this, that suppose we had a situation where on a smooth floor with respect to a wall, you attach this block, and initially the extension of the spring is 0, the initial velocity of the block is 0, and now you start applying a continuous force F naught like this in this. This is the situation at t equal to 0, and F naught is a constant force. So how we solve this SHM? Exactly like that only we'll solve the above one, but changing it to reduced mass. So now at some time t, you can see that. So if I assume that it has an acceleration in this direction also, it's fine. Or I can take the acceleration in the opposite direction, assuming kx is greater. So right now I'm assuming that F naught is still greater. So I have the equation net force F naught minus kx is equal to ma. And the way I've written here, it is plus T2x by dt square. So substituting that over here, you can see you're getting T2x by dt square as minus T by mx plus F naught by m. So it is of the type minus omega square x plus c. So the moment it is like this, from my mathematical analysis, I know that x will be some amplitude into sine omega t plus some phase constant plus c by omega square. Okay. Now I can see that x at t equal to 0 was 0. That means e sine phi plus c by omega square is 0 here. And I can also see that v at t equal to 0 was 0. That means dx by dt at t equal to 0 is 0. That means d omega cos phi is 0. So again, from these two equations, you can see that cos phi should be 0 and sin phi should be a negative quantity. That means phi should be minus pi by 2 or 3 pi by 2, whatever you write it as. So, and your e will become nothing but c by omega. So your x will become e into 1 minus cos omega t. Where you can see that x will range between 0 and 2. This is your maximum x. This is your minimum. So the spring never compresses in this case. So x maximum is 2a, which is 2c by omega square, which is basically 2f by k. We calculate what 2f by k. Omega square is k1. So this is very obvious result, which otherwise also you can understand from work energy. So when the kinetic energy becomes zero, x becomes maximum. You can understand it from an SHM point of view. So now you can relate this with the previous one, where you just treat the center of mass like a wall, and on either side you have two blocks doing this. But the formula for omega square changes. It comes in terms of reduced mass. The trick is the moment you see this secondary form of SHM, minus omega square x plus some constant, to understand that your equation of x is like this, where the mean position or equilibrium position is at x equal to c by omega square, which in this case will be f by q. So that is when kx is balancing out. Okay. So also in terms of graph, your x versus time here. You look like this. It vary between 0 and 2a. Half a cycle is gone to maximum displacement. One cycle is back to 0. So the previous thing, you can now relate it like this, that once you looked at the center of mass frame, it was traveling like this at ECM. So in that non-inertial frame, just treat the center of mass as if it were a wall. So on one side, you have a block on which there is some external force, let's say F2, which is continuous. Now that F2 is actually becoming the vector sum of this and pseudo force. And there is Kx like this. And on M1, there is F1 acting like this, which was nothing but M1 ACM, pseudo force, and Kx like this. But now you replace your Kx with, if this displacement was x1, it is K into M1 plus M2 upon M1 times x1. And here you replace Kx. If this displacement was, this is x1 and that one is x2. and this kx you replace it with k into m1 plus m2 upon m2 times x1. So this is doing an SHM with respect to the wall of that term. X1 is equal to P1 into 1 minus sine omega t. And this is doing an SHM with respect to the wall of, so just interchange X1 and X2. One minus cos. Solve that whole thing. So rather than that, actually you start with this, that when you solve this, you get d2x2 by dt square is equal to minus omega square x2 plus some constant. And here when you solve d2x1 by dt square, you get minus omega square x1 plus some constant. So your x2 will be equal to some amplitude into 1 minus cos omega t. And here your x1 will be some amplitude into 1 minus cos same omega. And that omega is given by that formula, square root of k divided by reduced base. So this is the shortcut that you can now know. When you remember all this analysis from before, you can directly understand this as a shortcut. Okay, so I hope this is clear. So SHM and oscillations involve a lot of trick-based questions like this, and I hope all this is clear to you. Right? Now there are a couple of questions which are symmetry trick-based again in magnetism that I wanted to discuss. So let's look at, or rather, it's tending towards EMI actually. So next example, we have something like this. Okay, so we have, let us say this is our XY plane. Because this is a Z axis. Now there's a current going like this, going to infinitely long conductor from Z tending to infinity to Y tending to minus infinity. So this current going all the way to infinity, and it's coming all the way from infinity above. We have this kind of conductor carrying current I. Now you consider an imaginary line joining these 2 points. Say P, which is at 0, L, 0, and Q, which is at L, 0, 0. So that's an imaginary line. In the xy plane. We want to find integration of B dot dl along that line P. How much this is? Okay. Just try this out, people. You should get that in terms of I, the current which is flowing through this infinitely long wire. Yes, Chakshu, your answer is correct for this. Very good. So the method that I would recommend is for this is superposition. For that, first we consider that suppose you add the infinite conductor along the z-axis. Suppose I add this. It was going all the way to infinity. And in that now I'm considering xy axis. Now if I consider this whole thing, I consider these points only. Then closed integral v dot dl for EQRS P would be equal to mu naught I, and integral v dot dl from P to Q would be 1/4 of closed integral v dot dl because of the symmetry. So that would be mu naught I by 4. This would be closed integral v dot dl from P to Q for this case. So now if you remove half of that, then you just consider a current just coming up to the origin. From plus infinity on the z axis. Then from P to Q would be half of what it is for the full one, full wire case. Because you removed half and they are symmetrically contributing same amount to magnetic field. So integral v dot dl from P to Q in this case will become mu naught I by E. So this is because of due to the current from z equal to infinity, z point tending to infinity to z equal to 0. Now we still have to show that the flux about this wire is how much. So we'll come to that. First make a note of this section. All right, this is clear. इसमें उसका exactly half होगा for this case. Okay. Now the second thing, consider the wire carrying current along the y-axis. That will create magnetic field anywhere on the xy plane in which direction? Along the z-axis or the negative z-axis. So if you consider a wire carrying current like this from the origin to minus infinity, at any point like this on the xy plane, any current element here will create a magnetic field which is, you can see like this, coming out of the plane. Create a magnetic field like this. Because from this current element, the R vector, so R and DL are in XY plane. So DB is along DL cross R. Whatever, but it is along PK. Therefore, B dot DL from P to Q will become 0 from the current along negative y-axis of y equal to 0 to y tending to minus C. So the contribution to B dot DL from this type of magnetic field created by that kind of wire becomes 0. So therefore, ultimately, we are left with just the first wire's magnetic field, and that is nothing but B dot DL integration is given mu naught I by E. So that should be the answer. Okay, so the final answer will become mu naught I by E. Entire arrangement. And you can also verify with the sign convention that it will be positive. Because P to Q along our loop originally, we were going clockwise. And the current was also going into the plane, looking into the XY plane. Okay, people, so hope all this was clear. Okay. So we'll conclude here today, and we'll continue with more problems next week. In the meantime, whatever doubts and questions you encounter, please send them to me via WhatsApp, and I'll give you some hints. And Chakshu, I think, has sent something just today morning or something. I haven't got a chance to see it. Something to do with, I think, Doppler's effect application. So I will send you the solution to that. And if the question is worth elaborating, then I will discuss it in the next lecture also. Okay. So that's it from my side today, guys, and all the best, people. Continue working hard and stay safe during this last phase of lockdown. Okay, Omkar. Thanks again. Thanks all of you. Thanks, Bhaskar, Chakshu, Omkar, and Ananya.